This is week 22, homework sheet, page 2, number 8. A voltaic cell is constructed using electrodes based on the following half reactions. Strontium ions, aqueous, plus electrons, yield strontium solid. Iron ions, aqueous, plus electrons, yield iron solid. What is the anode and what is the cathode in this cell? What is the standard cell potential? Now, the first thing we have to do is understand where oxidation is occurring and where reduction is occurring. So I've made my little chart here, and we're going to fill it in. You should be able to fill this in from memory with symbols that help you to remember what's happening in oxidation and reduction. So in oxidation, we know the old definition of oxidation is that oxygen is added. And whatever happens in oxidation, the opposite happens in the reduction. So if we add oxygen for oxidation, we subtract oxygen for reduction. Whatever happens with oxygen, the opposite is going to happen with electrons. So in oxidation, we subtract electrons. The other thing we have to be concerned with in oxidation and reduction is what happens to the oxidation numbers of individual elements. If they are being reduced, the oxidation number goes down. Reduction means going down. Oxidation number goes down. If they're being oxidized, it has to be the opposite, so the oxidation number will go up. If we remember this little chart, it can help us in determining what's happening at all of the different points in these reactions. See that I've started by drawing myself a little picture. The only thing I have in the picture thus far is two beakers, and I have a wire between the two beakers that shows electrons are going from one beaker to the other beaker. And this is what's happening in a voltaic cell. Now, let's name the two sides before we decide what type of ions belong on the two sides of the cell. So I started with the left-hand side. It doesn't have to be the left-hand side, it just has to be one of the beakers. I'm naming this side the anode. The anode starts with A, and I have a bunch of A words here to help you remember what happens at the anode. At the anode, electrons move away from the beaker. And so this side has to be the anode if I have the electrons going in that direction away from the beaker. The anode also has the metal with a higher activity, so I made an up arrow, active or more active metal. The anode is also the place where the metal that's reacting separates into individual ions. The electrons go in one direction, and the electrons are the anions. The cations that are left behind fall into solution. So the atom separates into electrons and whatever the characteristic cation is at the anode site. On this side, you see I've labeled it cathode. The cathode is the side of the voltaic cell that actually catches the electrons, so to speak, or tracks them. The anion and the cation come together to form an atom here, so they come together. This side is the metal that is actually less active, so it's the opposite of the active side, or the more active side. Now we have to decide which one of the two half reactions goes on either side. The first step is going to be to look at the reduction potential measurements There is a chart showing the standard reduction potentials measured in volts on page 693 of your book. And so for each of these two half reactions, we're going to write down what the standard reduction potential is. So if we look at these two half reactions, we see strontium has a standard reduction potential of negative 2.89. Iron has a standard reduction potential of negative 0.45. Whichever one is more positive is the one that has more potential to be reduced, hence the name reduction potential. So the one that's more positive, or if it is a positive number, the higher the positive number, the more likely it is, or the greater the probability that that will be reduced. If we look here, we see the one that's reduced is the one that has electrons added to it. So reduction has to be happening on this side where the electrons are being added into the beaker. So iron is the one that is closer to a positive number, so it's more positive. And that means this is the one that is going to be reduced. So we're going to put this equation into this beaker. So in this beaker, I've shown in my drawing this half reaction. We have iron cations, Fe2+, that are in the solution because the solution always has cations of whatever metal the electrode is made up of. Then we have electrons coming in through the wire toward this particular electrode. We said that at the cathode, the ions come together to create the metal. And so here we see the cation, which is the Fe2+, and the anion, or the negative ion, which is the electrons, coming together to create atoms of iron. Now what will happen, since atoms of iron are being created here at the electrode, is metal will build up on this particular electrode. So the little things I've drawn around the electrode are just atoms of metal being built up around this particular plate. So we know that iron is being reduced over here. Now we have to decide what's happening in this beaker. So you'll notice in this beaker, I've drawn strontium as the metal that this electrode is composed of. And I'm showing that the ions separate. So the strontium cation, Sr2 positive, falls into solution, and the strontium electrons go up through the wire toward the iron. Now strontium is a more active metal, and therefore strontium is the one that releases its electrons. Know that oxidation is occurring in this beaker. So oxidation is occurring here and reduction is occurring here. Now as these strontium cations fall off the electrode and the electrons pass through the wire, this electrode is actually being broken down and it's losing atoms of strontium, and so it will wear away and begin to crumble and get smaller, lose mass. Therefore, I've drawn these little half circles here showing as if somebody took a bite out of this piece of metal to show that it's losing mass. Now, if strontium is going through oxidation, we need to know the oxidation potential in volts rather than the reduction potential, because strontium is not being reduced, it's being oxidized. And the equation for strontium being reduced would be the reverse of this. So all we have to do is reverse the arrow and the sign. And now we're showing the oxidation of strontium and the oxidation potential. Now the question asked us what is the anode and what is the cathode, and we've shown that strontium is the anode and iron is the cathode. The question also asks us what is the standard cell potential, and in order to figure that out we have to add the reduction potential with the oxidation potential. So here's the formula. The standard potential of the cell is equal to the oxidation potential plus the reduction potential. The little degree sign or the little superscripted O just means that it's at standard conditions, standard temperature and pressure. So let's go ahead and add them. We can see that 2.89 plus a negative 0.45 equals 2.44. The measurement is in volts, and that is the answer for the standard cell potential. This is week 22, homework sheet page 2, number 9. Calculate the standard cell potential produced by voltaic cell consisting of a nickel electrode in contact with a solution of nickel ions and a silver electrode in contact with a solution of silver ions. Now, as always, the first thing we do is write the equation. The last problem had given us equations. This particular problem has only given us the two metals that the electrodes are made out of. So let's go ahead and write half cell reactions, or half reactions for these particular metals. So here we have the equation for nickel ion. We started with the ion that was given to us, nickel with a 2 positive. With the 2 positive, we know that it lost 2 electrons, and when we add them together, we get a nickel atom. It's a solid. Silver aqueous ion has only 1 positive, therefore we know only 1 electron goes with it to get solid silver. Now we look up in the book on page 693 to find out what the standard reduction potentials are for each of these two reactions. The nickel has a standard reduction potential of negative 0.26, and silver is positive 0.80. We know that more positive means that it is more likely to be reduced. And we look into our little chart that we've memorized how to draw, and we know that reduction means that electrons are added to it. So the one that's more likely to be reduced is the one that's actually going to have electrons added to it. That has to go on the side that the electrons are going into or being added into, the one that's catching the electrons, or the cathode, which catches electrons. So we're going to put the silver on this side. We drew silver here. I drew arrows showing that the silver ions in the solution and the electrons actually come together to form silver, more atoms of silver at this particular electrode, which is the cathode, which catches electrons. The ions come together. It's actually the less active metal, and we know that silver is not very active. And so we know that reduction is happening here because electrons are being added. I've drawn bumps coming out of the electrode showing that metal is being built up and the mass is increasing at this particular electrode. Now let's go over to this beaker, and since silver was here, we know that nickel has to be on this side. I've drawn nickel as the electrode on this particular side, which is the anode. The anode sends electrons away, and it also has the more active metal, and the metal separates into a cation and an electron, which is the anion. So I've shown arrows showing that the two ions are separating out and away from one another. the positive ions fall into solution, the negative electron goes through the wire toward the less active metal. Since this particular electrode is losing electrons, we know that oxidation is occurring here. And since oxidation is occurring and it's losing electrons and the cations of the metal are falling into solution, this electrode is being broken up or eaten away or reduced in mass. It's losing mass. So I'm making the little bumps to look like pieces are being taken out of this electrode. Now, we know that whichever reaction is going through oxidation, we need to change the direction of the arrow and the sign of the reduction potential to show oxidation. And now this is showing that nickel loses an electron and separates into a positive ion. So oxidation is occurring. Now the problem asks us what the standard cell potential is. And in order to find that, we have to add the oxidation potential with the reduction potential. So the standard potential for the entire cell is the oxidation potential added to the reduction potential. 0.26 plus 0.8 equals 1.06 volts, and that is the standard potential for this cell. This is week 22, page 4, number 26A. Which of the following has the greater tendency to lose an electron, zinc or chlorine ion? At first look at this, you might think that chlorine has an extra electron, which it does, and therefore it would be willing to lose that. But that's not true. When chlorine gains that electron, it becomes more stable. So it will take a lot of energy to take that electron away from chlorine. Zinc, on the other hand, is a metal, and zinc has all those electrons that are kind of swimming around all of the metal protons or atoms. And those electrons conduct electricity very well because they can move easily, and they're not as highly bound to the whole entire metal. Therefore, we can safely assume that the zinc will lose its electrons much more easily than chlorine. This is week 22, page 4, number 26B. Which of the following is the stronger oxidizing agent? Hydrogen ions or diatomic iodine? Now, if we're looking for an oxidizing agent, we're looking for something that can easily be reduced, because whatever is being reduced is causing something else to be oxidized, since oxidation and reduction always go hand in hand or work together in a reaction. So to find an oxidizing agent, we find something that can be easily reduced. And something that can be easily reduced can accept an electron very easily. Now again, you might see that hydrogen has a positive charge and think, okay, that's going to pull an electron to it very quickly. And it will pull an electron toward it, but will it do it more easily than iodine is the question. In order to figure that out, we have to look at the reduction potential chart on page 693 to see which one has a greater potential to be reduced. If we look at the chart, we see that hydrogen is the atom to which all reduction potentials are compared. Hydrogen is 0, and if it is more likely to be reduced than hydrogen, then it has a positive number. If it's less likely to be reduced than hydrogen, it has a negative number. So hydrogen's reduction potential is 0. The standard reduction potential of iodine is 0.54, so it's actually greater than hydrogen, so it has a greater possibility of being reduced. And since whatever is reduced causes oxidation in something else, it is an oxidizing agent. So iodine is more likely to be the oxidizing agent. Week 22, page 4, number 26C. Which of the following is the stronger reducing agent, lithium or diatomic fluorine? This time we're looking for a reducing agent. So that means it's whichever one is causing reduction. And since reduction is the opposite of oxidation, whichever one is going through oxidation causes reduction. Again, we're going to compare the reduction potential standards on page 693. Lithium has a negative standard reduction potential. Fluorine has a positive standard reduction potential. That means fluorine is more likely to be reduced. And if fluorine is more likely to be reduced, then lithium is more likely to be oxidized. And if lithium is oxidized, then it is the reducing agent.